9b, this is going to be a continuation of constrained optimization. This handout, by the way, is already in the Learning Hub, but this time we're going to be looking at multiple constraints. The approach we're going to be using for this is often referred to as the Kuhn-Tucker approach. I want to provide a little bit of background. We're actually going to shift back to our handout on Module 9a and look at our level curves again. Let's recall what we were doing with Module 9a was rooted in this concept. We have these indifference curves. Utility was equal to 5, 10, 15, and 20. And what we were looking to do was to maximize the utility. We know that as we increase our utility, the curves go further in this direction. Now, we had a constraint added to it. What we could start to visualize using these graphs, we could see that utility is equal to 5, for instance, would be within the constraint. It's all under our constraint line is everything that is acceptable. That a utility of 10 would be acceptable as well, but that a utility of 15 would not be achievable. I shouldn't have been saying acceptable, I should have been saying achievable. A utility of 15 would not be achievable within this constraint. That the maximum utility was between 10 and 15. We could take that a step further, and when we find our maximum utility, it is the curve that just touches this line. It just touches this line. We have one combination of x1 and x2 in which we would be meeting this constraint, and that would be the highest utility that we could get. In this case, that utility was 14.1421. Now onward to 9b. What is this going to look like when we have two constraints? I'm going to do, as an example, is I'm going to start with a function u is equal to xy, and I've plotted that here. You can see utility of 200, 350, 500. My pen is too thick right now. The pink line is 500, and the purple line here is 650. So my utility, again, is increasing in this direction. When a function is subject to more than one constraint, what we're going to have to do is we're going to have to determine which constraint is binding. Now that might seem a little bit strange. So I'm going to show us a few scenarios to help us understand what that means. I'm going to be taking this utility and trying to optimize it. So you guys got the general shape of our utility here? Our first scenario here is where we're going to have two constraints. Constraint 1, here in pink, is x plus 1.5 y is less than or equal to 39. Constraint 2, highlighted in blue here, is 2x plus y is less than or equal to 60. Remember that our function here is u is equal to xy. Now focusing first on constraint 1. Imagine I tried to do my whole optimization process just looking at constraint 1. I did the whole Lagrange process just using constraint 1, ignoring constraint 2. If I were to plot all of these together, I did my optimization, I found where my utility was tangent to constraint 1 being in red here, and I can see that this would be the maximum utility. There's one combination of x and y values that this utility would touch. The green line is tangent to the red line. See how that would be the maximum utility, that this green line represents the maximum utility, that utility of 253.5. This would be the highest utility that would meet our red constraint. Now we're going to double check that our blue constraint, our second constraint, is also satisfied. This is the highest utility that will satisfy our first constraint, but will our second constraint be satisfied? Well, here our blue line is our second constraint. So this blue line defines the boundaries for what is acceptable. Is that dot is that XY combination, this point right here, is that within the blue area? Yeah, it is. It's under the blue line. So our point where we would be looking at our maximum utility, this giant dot I created of XY, it is within both the blue constraint and the red constraint. So based on this, if I had done my optimization using just constraint 1, I will have solved this problem. This is the maximum utility that satisfies constraint 1, and it coincidentally satisfies constraint 2. This is the highest utility we can get. We have now solved our optimization of this problem. Now let's imagine a different hypothetical. Imagine that we had this same scenario, but instead of optimizing with constraint 1 and ignoring constraint 2 to begin with, that's what we had previously done, this time I'm going to approach the problem by trying to optimize with constraint 2 and ignore constraint 1. What would the outcome be if I approached the problem that way? And this is going to happen. Sometimes you choose the other constraint to start your optimization with. So this time I'm saying I start my optimization. I ignored constraint 1. I'm doing my analysis with constraint 2. What would have happened? Well, I would have done my optimization with constraint 2, and I would have found a different optimal utility level. We would see that if I were working with constraint 2, this blue line here, the maximum utility would be where it just touches, where our utility line just touches our constraint, and that would be corresponding to a utility of 450. By this approach for my analysis, I would have found my optimal XY coordinate to the maximum utility corresponding to constraint 2. Let's examine to see if this optimal XY value is within constraint 1. So this would be my optimal XY value. Is that within constraint 1, the red line? So constraint 1 is defined by this red line. The region that would be satisfied is over here. So our optimal XY value is not within that constraint. Thus, we are not meeting our second constraint. Would this be an acceptable solution? No, it would not be an acceptable solution. This meets constraint 2, but not constraint 1. Therefore, it is no good. Versus this solution, we were good with constraint 1, we were good with constraint 2, it was good overall. So we have a formalized process for which we do our analysis. This is what's going to happen with our Kuhn-Tucker optimization. We're going to recognize that we have two constraints. We're going to set up our Lagrange equation. This is a function we want to optimize. This will be our first constraint. This will be our second constraint. So constraint 1 there in pink, constraint 2 in blue. What we do to begin with is we ignore one of the constraints. For example, we would ignore the second constraint. Essentially, we make this value equal to 0. Then we do our whole Lagrange process, essentially just using this part of the equation. That would have gotten us a solution that we saw right here, optimization with constraint 1. Then what we do is we do a check. Once we get those x, y values, we have to confirm the assumption from step 2 is satisfied. We have to double check that this second budget, this blue budget, is satisfied. And that's what we did over here. We did our optimization with constraint 1, and then we double check that it's within constraint 2. Optimization with constraint 1, double check it's okay with constraint 2, and then we're happy with the solution. Now, what happens if we had done it differently? What if we had started with constraint 2? What would have happened is I would have done my optimization with constraint 2. I would have been happy. But then I would have checked to see if it satisfies constraint 1, and I would have said, no, it does not satisfy constraint 1. So I would then go about redoing my analysis. I'm going to stop my analysis, reject this, and then I will do my optimization with the other constraint. So if the constraint was satisfied, like when we did it with option 1 first, that's great. But if that constraint is not satisfied, we have to do another step. And then we would assume the other constraint is applicable. So these are two hypotheticals. At the end of the day, what if I had ordered these differently? What if I had flipped those around, or you had pulled the information out in an opposite fashion? If you had started this way, you would be done. You would be done your problem. But 50-50 chance you chose the right constraint to start with, isn't it? If you had started with constraint 2, then you would have gone, uh-oh, that didn't work. I better switch to using constraint 1. No, you don't always have to. So you do your optimization with one constraint, then you look at your X and your Y values. If it satisfies the second constraint, you're happy and you move on. However, if it doesn't, like in this one scenario on the right, then you have to switch gears. Then you have to go back to the other constraint and do your optimization. Another scenario here, I have new constraints, same function, u is equal to xy, but this time I have a different constraint 1. So I do my optimization with constraint 1, and what happens? Uh-oh, that's not within constraint 2, is it? So what do? So I met constraint 1, and then I look at constraint 2, and I'm not happy. So I then do the optimization with constraint 2. So I do my optimization with constraint 2, and now I'm within constraint 1. So constraint 2 has been met. Constraint 1 has been met. I'm happy and I'm done. So in this scenario 1, where constraint 1 made us happy, and for both, we would call constraint 1 binding constraint. With our second scenario, by optimizing with constraint 1, both were not satisfied. But by optimizing with constraint 2, both were satisfied. So we would call constraint 2 binding. Constraint 2 is more limiting. No, you do not have to graph it every time. You can do this mathematically. What you do is you find your xy values, and then you plug those into the other constraint. So here, let's say I optimize with constraint 1, and I get x is equal to 25, y is equal to 25. I plug those into the constraint 2, and I find out that, that becomes 75. 2x plus y is going to be equal to 75. That is not less than 60. So I fail the constraint mathematically. Now I'm going to show you one more potential scenario we're going to run into. And I'm showing you this graphically at first because a lot of your information in econ is going to be presented graphically like this. They're going to jump to the end. They're not going to show you the whole mathematical proof. And so you need to be able to read these graphs. Now, scenario 3 is when both constraints are going to be binding. So let's look at this. Here I have optimization done with constraint 1. When I did my optimization with constraint 1, I get my xy value right here. That's where it's tangent to constraint 1. If this is my xy value, am I under the blue line? No. Have I met constraint 2? No. So based on constraint 1, this is my optimal xy value, but it does not satisfy constraint 2. So we're not happy. So then I move on to constraint 2. I do my analysis. I discover we have an optimal value right here. So this is my XY value that is optimal for constraint 2. Is constraint 1 being met now? Nope. Constraint 1's all the way over here. Constraint 1 is not being met. So again, we're not happy. So what we would do at that point, we have to use both constraints. Utility could not be maximized by optimizing based on constraint 1 alone, nor constraint 2 alone. Thus, we have to optimize based on both constraints. We always try to optimize with one constraint first, but if those fail, we go to 2 constraints. And where that sweet spot is going to be, where that utility is going to be maximized, is at the intersection of our 2 constraints. So we solve it by finding the intersection of the 2 constraints becomes our XY value. So that's the theory of what we're going to be doing. So there's our lesson in pictures. Now we actually have to do this mathematically.